What if what holds our galaxy, the clusters of galaxies, and ultimately the entire universe together, is completely invisible? For centuries, humanity has looked up at the sky, admiring the beauty of stars and galaxies, believing that what we saw was all that existed. However, the reality is much more mysterious. Most of the matter in the cosmos neither emits nor reflects light, cannot be seen even with the most powerful telescopes, and its presence can only be inferred from its gravitational effects. How is it possible that something so fundamental remains hidden from our eyes? What hidden force dominates the universe from the shadows? Dark matter is one of the greatest enigmas of modern science. Astronomers realized, while studying the movement of galaxies and the dynamics of clusters, that the amount of visible matter simply wasn't enough to explain what they observed. It's like trying to weigh a truck just by looking at the lights turned on. The light is there, but the true weight is hidden. What exactly is this invisible matter? Why can't we detect it directly? And above all, how do we know it's really there if we've never seen it? A key scenario where this enigma becomes more evident is the Coma Cluster, a gigantic congregation of galaxies located over 300 million light-years from Earth. It was precisely in this cluster where the first solid hints of the existence of dark matter came to light, revolutionizing our understanding of the universe. In Coma, galaxies move in a way that defies all logic, if we only consider visible matter. It's like watching a group of people dance in the dark and realizing, by the sound of their footsteps, that there are many more dancers than can be counted. The paradox of dark matter in the Coma galaxy raises a crucial question. What is the universe really made of? Could it be that everything we know, from stars to planets and ourselves, is just a small fraction of the true cosmic story? Join me as we explore how the study of the Coma galaxy confronts us with this paradox, and why solving it could forever change our view of the cosmos. Dark matter is one of the greatest enigmas of the universe. How is it possible that most of the mass of the cosmos is invisible? When we talk about dark matter, we refer to a type of matter that does not emit, absorb, or reflect light, making it completely undetectable through traditional astronomical observation methods. However, its existence is fundamental to explain the behavior of galaxies, their movement, and the large-scale structure of the universe. If the universe were a theater, visible matter would be just the scenery and the actors, while dark matter would be the mysterious scaffolding that holds everything up from the shadows. Why are scientists so convinced that something they cannot see exists? The answer lies in the effects that dark matter has on its surroundings. For example, galaxies spin so fast that according to the amount of visible matter, they should disintegrate and scatter into space. But they don't. Something invisible and very massive keeps them together. It's as if you were watching a wheel spin much faster than its structure would allow, and you discover that there is a hidden force holding it up. That force is the gravity generated by dark matter. What do we really know about the nature of this mysterious matter? So far, dark matter has not been directly detected. It does not shine, does not heat up, does not interact with light or electromagnetic fields. It only becomes evident through its gravitational effects. Its presence is inferred by observing how stars behave within galaxies, how galaxies cluster into groups, and even how the light from distant objects bends when passing near large concentrations of invisible mass. It's like trying to deduce the shape of a sculpture covered by a cloak, observing only the wrinkles and folds in the fabric. Could dark matter be composed of particles still unknown to physics? That is the big question. The most accepted theories suggest that dark matter is made up of particles that barely interact with ordinary matter beyond gravity. Names like WIMPs or axions have been proposed, but so far none have been confirmed. What we do know is that dark matter accounts for approximately 85% of all the matter in the universe. Without it, the cosmic structure as we know it would be impossible, and the history of the universe would have been very different. Dark matter remains a veil that challenges our understanding, a constant reminder that the cosmos still holds secrets to be discovered.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
If we look at the sky on a clear night, we might think we are gazing at most of the universe. However, what if I told you that everything we see, from the brightest stars to the farthest galaxies, is just a tiny fraction of what really exists? Visible matter, the kind that emits or reflects light, makes up only a small part of the total. But how much exactly? According to the latest calculations, ordinary matter accounts for less than 1/20th of the matter in the cosmos. The rest is made up of a mysterious substance that neither emits, reflects, nor absorbs light: dark matter. This distinction is much deeper than it seems. It's as if we can only see the foam on the surface of an immense ocean, while everything that supports and shapes that sea remains hidden beneath the waves. Thus, the visible universe is just the tip of the iceberg. The invisible, although we cannot observe it directly, fundamentally influences the movement of galaxies, the formation of clusters, and the overall structure of the cosmos. How do we know it's there if we can't see it? The answer lies in gravitational effects. Galaxies spin, and clusters remain bound together, thanks to a mass that, although invisible, leaves clear traces in the behavior of the universe. Isn't it fascinating to think that most of the matter surrounding us is, in fact, completely invisible to our eyes and telescopes? If visible matter is like the lights of a city seen from afar, dark matter would be the vast network of roads, buildings, and structures that shape it, yet remain shrouded in darkness. Without that invisible matter, galaxies simply could not hold together. They would spin so fast that they would disintegrate. This paradox led scientists to wonder, what is the universe really made of? And why is there so much that we cannot see? The quest to understand the invisible universe is one of the greatest challenges of modern science. Although dark matter does not interact with light, its influence is so powerful that it shapes the fate of entire galaxies. Today, we know that visible matter, all the planets, stars, and clouds of gas, is just a small note in the cosmic symphony. The true score is written in dark matter, that silent presence which, although we cannot see, determines the fate of everything we can observe. Therefore, understanding the difference between the visible and the invisible universe is essential to unraveling the deepest mysteries of the cosmos. How did the mystery of dark matter begin? To answer, we must travel back to the 1930s, when astronomers started to notice something strange in the behavior of the cosmos. Back then, it was thought that the gravity of stars and visible gas was enough to hold galaxies and their clusters together. However, some observations intriguingly contradicted this assumption. The first major clue emerged when scientists analyzed the speed at which galaxies rotate and the pace at which they move within large clusters. If only the matter we can see existed, those structures should disintegrate, as if you were trying to tie a bunch of balloons with a thread that was too weak. However, the galaxies remained clustered, defying any calculations based solely on visible matter. What was holding these cosmic giants together? One of the key moments in this story was led by Swiss astronomer Fritz Zwicky. While observing the Coma Cluster, Zwicky noticed that the galaxies within the cluster were moving so fast that, according to known laws of physics, they should escape and disperse into space. But that wasn't happening. Zwicky then proposed the existence of an invisible mass, which he called dark matter. It was a revolutionary idea, a kind of cosmic glue that kept galaxies together, even though no one could see or directly detect it. Over the following decades, other astronomers began to find similar evidence in different parts of the universe. For example, Vera Rubin in the 1970s studied the rotation of spiral galaxies and discovered that the stars at the edges rotated as fast as those in the center, something impossible if only luminous matter existed. Isn't it astonishing to think that most of the universe is made up of something we cannot see, yet whose existence is essential for the cosmos to make sense? Thus, piece by piece, the story of the discovery of dark matter was constructed, opening one of the greatest mysteries of modern science. In 1933, a Swiss astronomer named Fritz Zwicky asked a seemingly simple question: why do the galaxies in the Coma Cluster not disperse into space if the gravity of visible matter seems insufficient to keep them together? Zwicky, known for his eccentric character and unconventional thinking, dared to challenge the accepted ideas of his time. His concern arose from observing the dizzying speeds at which the galaxies moved within this cluster. They were so high that, if only the visible matter existed, the cluster should have disintegrated long ago. What did Zwicky then discover that forever changed our view of the universe? By comparing the amount of light emitted by the galaxies in Coma with the mass needed to maintain their gravitational cohesion, he realized there was a staggering difference. It was like trying to keep a group of unruly children together with just paper strings. It simply wouldn't work unless there was an invisible force or substance acting secretly. Zwicky named this mysterious substance dark matter, a form of matter that does not emit detectable light or energy, but whose presence is revealed by its gravitational effects. Why did the Coma Cluster become the perfect setting for this discovery? It's no coincidence. The Coma Cluster is one of the most massive and dense known, composed of thousands of galaxies. Zwicky applied the virial theorem, a mathematical tool that allows the calculation of the total mass of a system based on the speed of its components. In doing so, he found that the total mass of the cluster was at least 10 times greater than the visible mass. This discrepancy could not be explained by the stars, gas, or dust that could be observed. Something else had to be there, hidden from view. Zwicky's boldness was such that, at the time, many colleagues dismissed his hypothesis as mere eccentricity. However, today we know that his intuition was correct. His analysis of the Coma Cluster not only inaugurated the modern search for dark matter, but also forced us to accept that most of the universe is composed of something we cannot see. It is fascinating to think that a seemingly simple question, posed by a curious astronomer, unleashed one of the greatest revolutions in modern cosmology. How far can our understanding go if we continue to look beyond the obvious? What makes the Coma Galaxy so special? And why has it captured the attention of astronomers for decades? The answer begins with its environment. The Coma Galaxy is not alone. It is part of one of the most massive and studied galaxy clusters in the nearby universe, known as the Coma Cluster. This cluster is like a cosmic metropolis, where thousands of galaxies coexist in the same neighborhood, interacting through gravity in a ballet that defies imagination. But what is this galaxy really like? What are its main characteristics? The Coma Galaxy, also frequently identified as NGC 4874, is a giant elliptical galaxy, one of the brightest and most massive in the cluster. We should not imagine it as an elegant spiral like the Milky Way, but rather as an immense cloud of stars without defined arms, with a rounded and diffuse shape. Why is this detail relevant? Because elliptical galaxies, like Coma, are often found in dense regions of the cosmos and are the result of collisions and mergers with other smaller galaxies. Thus, the Coma Galaxy is a true testament to the violent and dynamic history of the universe. An intriguing question arises: what other peculiarities does this environment have? The Coma Cluster, where the Coma Galaxy resides, houses not only giant galaxies, but also a large number of dwarf galaxies, clouds of hot gas, and, of course, an overwhelming amount of dark matter. In fact, the hot gas bathing the cluster emits X-rays, revealing temperatures of millions of degrees, much higher than in most regions of space. But the most impressive thing is that despite all the visible matter, most of the mass of the cluster remains invisible to us. This makes it a natural laboratory for studying the mysteries of the universe. And how does the environment of the Coma galaxy influence its behavior? The galaxies within the cluster constantly interact, experiencing tidal forces, mergers, and even the destruction of their original structures. The Coma galaxy, as one of the most massive, exerts a strong gravitational influence on its neighbors and helps maintain the cohesion of the cluster. At the same time, its own history is marked by countless cosmic encounters, making it a key piece in understanding how galaxies evolve in extreme environments. Thus, the Coma galaxy is much more than just a simple collection of stars. It is a central protagonist in the grand drama of dark matter and galactic evolution. What makes the Coma Cluster so special in the vast universe? To understand this, let's think of a city filled with skyscrapers, where each building is a galaxy. The Coma Cluster is precisely that, a gigantic grouping of galaxies, a cosmic metropolis where thousands of galaxies coexist in a relatively small space of the cosmos. But how is this galactic city organized? Unlike what we might imagine, the galaxies within the Coma Cluster are not distributed evenly. The highest concentration is found in the core of the cluster, where the galaxies group together in a kind of dense swarm. Here, giant elliptical galaxies dominate, such as the well-known NGC 487 and NGC 488, which act as true gravitational centers. As we move away from the core, the galaxies become increasingly dispersed, forming a less dense halo, but equally fascinating. But what keeps so many galaxies together in such a small space? If we only count visible matter like stars, planets, and gas, gravity would not be enough to prevent the galaxies from escaping from one another. This is where the mystery of dark matter comes into play. It is estimated that more than 90% of the mass of the Coma Cluster is composed of this invisible substance, which acts as a cosmic glue, holding the whole structure together despite the speed at which the galaxies move. The Coma Cluster not only contains galaxies, but also enormous amounts of hot gas, so hot that it emits X-rays detectable from Earth. This gas, although invisible to the human eye, is essential for understanding the structure of the cluster, as its distribution reveals the presence of gravitational wells created mainly by dark matter. Thus, the structure of the Coma Cluster is much more than a simple gathering of galaxies. It is a complex web where the visible and invisible interact, shaping one of the most enigmatic natural laboratories in the universe. Can such a massive cluster remain stable for billions of years? The answer seems to be written in the distribution of its matter. Dark matter forms a framework upon which the entire visible structure rests. Without this invisible support, the Coma Cluster would be nothing more than a scattered group of galaxies, unable to sustain the extraordinary architecture that astronomers study today. Ultimately, the structure of the Coma Cluster is a testament to the delicate balance between what we can see and what is yet to be discovered in the cosmos. How do galaxies really behave within the Coma Cluster? At first glance, we might think they group together peacefully, floating in space like leaves on a pond. However, the reality is much more dynamic and chaotic. The galaxies within Coma move at extraordinary speeds, some exceeding 1,000 kilometers per second, as if participating in an endless cosmic race. But what invisible force keeps this galactic swarm together, preventing the galaxies from shooting off into intergalactic void? To understand this, let's imagine a huge amusement park where roller coasters, instead of following a fixed track, move at full speed in all directions, crossing paths, brushing against each other, and sometimes even colliding. In the Coma Cluster, each galaxy is like one of those cars, accelerating and braking under the influence of the cluster's collective gravity. If we only counted the visible mass, the stars, gas, and dust, these movements would be impossible to explain. Gravitational attraction wouldn't be enough to keep them together. The galaxies would escape the cluster in just a few 100 million years. This is where the true paradox arises. Why doesn't that dispersion occur? The explanation is intriguing. There is a vast amount of invisible mass, known as dark matter, that acts as a gravitational glue and keeps the cluster cohesive. The dynamics of the galaxies within Coma were one of the first hints that there must be something more than visible matter. If we analyze how they move, how they accelerate, and how they change direction, calculations show that the total mass is at least 5 times greater than what we can detect with traditional telescopes. But how are these movements studied? Astronomers measure the redshift and blueshift in the light from the galaxies, a kind of cosmic radar that reveals the speed at which they are approaching or receding from us. This data allows us to reconstruct the choreography of Coma, a system in constant agitation, where galaxies orbit around a common center of gravity, mainly dictated by dark matter. The speed at which they move demonstrates that visible gravity is not enough, and that most of the mass remains hidden from our eyes. In summary, the internal dynamics of the Coma Cluster is a complex and accelerated dance, impossible to understand without the presence of dark matter. It is thanks to the meticulous study of these movements that scientists have been able to infer the existence of this mysterious substance, which shapes the fate of galaxies and challenges our understanding of the universe. What other secrets lie behind the swift turns of Coma? The search continues, and each orbit brings us a little closer to the heart of this cosmic enigma. The mass paradox in the Coma Cluster is one of the most fascinating and perplexing enigmas of modern astronomy. It all began when astronomers tried to calculate the total amount of matter present in this gigantic group of galaxies. What happens if we add up all the visible light emitted by stars, gas, and dust? The result is surprising. Luminous matter represents only a tiny fraction of the mass needed to explain the behavior of the cluster. It's like trying to weigh a truck by only looking at the wheels and realizing that most of the weight is missing. So where is the mass that holds the Coma Cluster together? By studying the speed at which galaxies move within the cluster, scientists discovered something unexpected. According to the laws of physics, if only visible matter existed, galaxies should escape the cluster at high speeds, like cars shot across a frictionless ice rink. However, they remain gravitationally bound, spinning at much higher speeds than what the gravity of visible matter could allow. The only possible explanation is that there is an immense amount of invisible matter, a kind of cosmic glue that keeps everything together. This staggering difference between the mass calculated from visible light and the total mass deduced from gravitational behavior is known as the mass paradox. How can it be that 90% of the cluster's mass emits no light or any detectable radiation? It's like attending a theater where you can only see a handful of actors on stage, but the shadows and effects on the set make you suspect that there is a much larger cast hidden behind the curtains. The mass paradox in Coma not only challenges our understanding of the universe's content, but also puts fundamental laws of physics in jeopardy. If dark matter truly exists, then most of the cosmos is made up of something completely unknown, which only reveals its presence through gravity. Solving this mystery is one of the greatest scientific adventures of our time, because understanding the hidden mass of Coma could be the key to deciphering the workings and ultimate fate of the universe. What if we told you that gravity can reveal secrets that our eyes could never see? At first glance, it seems like we should only worry about what shines in space, stars, planets, nebulae. But the reality is much more complex. Gravity, that invisible force that keeps the Earth orbiting around the Sun and the Moon dancing around us, is also the best ally of astronomers to uncover what the universe hides in the shadows. If only the matter we can see existed, the movements of galaxies and clusters should be perfectly predictable. However, that is not the case. Why do the galaxies within the Coma Cluster move so fast, as if being pushed by a mysterious force? Calculations based solely on visible matter do not add up. If we only took into account the stars and gas we can observe, the cluster should disintegrate, as the visible gravity is not enough to hold it together. It's like a group of people trying to hold hands on an ice rink. If there isn't enough force among them, the group would disperse. But in the case of the Coma Cluster, the group remains united, as if there were a hidden force, much more powerful, keeping them cohesive. Gravity acts like an unyielding detective. When scientists measure the speed at which galaxies rotate or move within a cluster, they realize that this speed cannot be explained solely by the visible mass. It's as if we found a roller coaster in an amusement park that moves much faster than its visible motors would allow. Inevitably, we would suspect that there is a hidden mechanism driving it. Thus, astronomers deduce that there must be a large amount of invisible matter whose presence is only revealed through the gravitational effects it produces. Gravitational evidence is compelling. It is not a hunch or an optical illusion. It is the result of equations, measurements, and observations repeated over decades. This excess gravity, which cannot be attributed to luminous matter, is the main clue to the existence of dark matter. It's as if the universe is sending us a coded letter, and gravity is the key to deciphering it. Thanks to this phenomenon, scientists have been able to map entire regions of the cosmos where dark matter dominates, even though they have never seen it directly. Without gravitational evidence, dark matter would be mere speculation. With it, it becomes one of the greatest enigmas of modern physics. Is it possible to see something that, in theory, is invisible? The answer, surprisingly, is yes, and dark matter in the Coma Cluster is proof of this. How? Thanks to a fascinating phenomenon known as gravitational lensing. When we talk about lenses, we usually think of the glass in glasses or a magnifying glass. But in the universe, gravity itself can bend the path of light, acting as a gigantic cosmic lens. When light from distant galaxies passes through the Coma Cluster, its path is distorted by the enormous amount of mass present, even if that mass is invisible to us. What does that distortion reveal? It gives us an indirect map of dark matter, allowing us to see its effects even though we cannot observe it directly. But why is this effect in Coma so relevant? The Coma Cluster contains thousands of galaxies and such a large amount of mass that the light passing through it bends remarkably. It's as if we were looking through an irregular glass. The background image is distorted, multiplied, or even stretched into strange arcs. Astronomers can study these distortions and, using equations from general relativity, reconstruct the distribution of the mass that causes this effect. The surprising thing is that, when making these calculations, the visible mass, the one we can count in the form of stars, planets, and gas, is not enough to explain the intensity of the lenses. Most of the mass that bends the light is invisible. It is dark matter. This method has been fundamental in confirming that dark matter is not just a mathematical hypothesis, but a tangible reality whose traces are throughout the universe. Gravitational lenses in Coma have been studied for decades, and thanks to them, the distribution of dark matter has been mapped with astonishing precision. Scientists have found that dark matter concentrates around the largest galaxies in the cluster, but it also forms a kind of network that connects the entire cluster, as if it were an invisible scaffolding that gives cohesion to the galaxies. And what impact does this discovery have on our understanding of the cosmos? Knowing how dark matter is distributed thanks to gravitational lenses helps us understand why galaxy clusters, like Coma, can remain bound together despite the speed at which the galaxies within them move. Without the additional mass provided by dark matter, gravity would not be sufficient to maintain the structure of the cluster. Thus, every time the light from a distant galaxy bends as it passes through Coma, it is whispering a secret to us. In the universe, there is much more than meets the eye. How is it possible to measure the mass of something we cannot see? This question has fascinated astronomers for decades, especially when it comes to galaxy clusters like Coma. The key lies in observing the movement of galaxies within the cluster. If the galaxies are traveling too fast, they would escape the gravitational pull of the cluster and it would disperse. However, the surprising thing is that by measuring the speeds of these galaxies, it is found that they are moving much faster than they should if only visible matter existed. What keeps the cluster together? Where does that extra gravity come from? To answer this enigma, astronomers turn to the famous virial theorem, a mathematical tool that relates the kinetic energy of a system to its gravitational potential energy. In simple terms, if we know the speeds of the galaxies and how they are distributed, we can estimate how much total mass is needed to keep them together. It's like observing a swarm of bees. If they are flying very fast and remain clustered, we would assume there is something strong enough holding them together, even if we don't see that glue directly. The process involves measuring the Doppler effect in the light from the galaxies, which reveals whether they are moving closer or further away and at what speed. By analyzing hundreds of these speeds, scientists determine the average speed and the dispersion of speeds within the cluster. With this data, they apply the virial theorem to calculate the total mass needed for the cluster not to disintegrate. And what is the result? The calculated mass is often several times greater than the sum of all the stars, planets, and visible gas in the cluster. This monumental mismatch between visible mass and total calculated mass is one of the most compelling pieces of evidence for the existence of dark matter. The observed gravity simply does not match what can be seen. Thus, the study of the speeds of galaxies in clusters like Coma not only allows us to estimate the total mass, but also reveals the presence of an invisible and mysterious substance that dominates the universe. Will we ever be able to directly see that dark matter? For now, we can only continue calculating, observing, and marveling at the extraordinary cosmic balance that holds such colossal structures together. Have you ever wondered how we know where dark matter is if we can't see it? Although dark matter is invisible to our eyes and telescopes, its presence is revealed through its gravitational effects. In the Coma Cluster, astronomers have managed to map how dark matter is distributed by observing the movement of the galaxies that compose it and analyzing how light bends when passing near enormous concentrations of mass. It's like trying to discover the shape of a sculpture covered by a sheet, feeling its contours without being able to see it directly. The Coma Cluster is one of the most studied examples in the universe to understand the distribution of dark matter. This cluster contains thousands of galaxies, but the surprising thing is that the visible mass of all of them together is not enough to explain the speed at which they move. This is where dark matter comes into play. Scientists have calculated that most of the mass of the cluster does not come from stars, gas, or dust, but from this invisible substance that acts as a gravitational glue, holding everything together. But how is this dark matter distributed within the Coma Cluster? Thanks to techniques like gravitational lensing studies, astronomers have been able to create detailed maps of its presence. They have discovered that dark matter is not concentrated only in the center, but forms vast halos that envelop both individual galaxies and the cluster as a whole. These halos can extend far beyond the region where the light from the galaxies is visible, as if dark matter forms a kind of invisible skeleton upon which the structures of the universe are built. One of the most intriguing curiosities is that the distribution of dark matter in Coma is not perfectly uniform. There are regions where it seems to accumulate in greater amounts, likely due to past collisions between galaxies or even between entire subclusters. This pattern suggests that dark matter plays a key role in the evolution and history of galaxy clusters. Despite all these advances, the complete map of dark matter remains an enigma. We know its footprint, but its true nature still eludes us, like the shadow of something gigantic moving beyond our sight. For decades, the big question has been, what is dark matter really made of? We know it accounts for most of the mass of the universe, but its true nature remains one of the deepest enigmas of modern science. When we try to identify it, we encounter an even greater mystery. Why can't we detect it with our telescopes, not even with the most powerful ones? The key is that dark matter, unlike ordinary matter, does not emit, absorb, or reflect light. It is invisible to all optical instruments. But then, what could compose this cosmic ghost? Scientists have proposed several fascinating theories. One of the most popular suggests that dark matter is made up of exotic particles that we simply do not know, known as WIMPs, which stands for weakly interacting massive particles. Imagine a universe filled with particles that pass through our bodies and everything around us without leaving a trace, as if they were much more massive and even more elusive neutrinos. But what if these are not the ones responsible? Then the hypothesis of axions arises, incredibly light theoretical particles that would behave more like waves than like particles. If they existed, they could fill space in such a subtle way that even the most advanced detectors would barely notice their presence. Now, could dark matter be made up of larger objects, like primordial black holes? Some scientists have raised the possibility that shortly after the Big Bang, tiny black holes formed that now float through the universe, invisible, but with enough mass to explain the gravitational effects we detect. However, exhaustive searches in the cosmos have not found conclusive evidence to support this idea. This lack of direct evidence forces us to look for clues in the most unexpected places, even in high-energy particle collisions in underground laboratories around the world. But the difficulty in uncovering the composition of dark matter goes beyond the experimental. Each new theory opens the door to even more complex questions. Are there unknown forces in nature? Could dark matter be a collection of particles and not just one? Are we perhaps limited by the very physics we know? Solving this enigma would not only help us understand dark matter, but it could also reveal fundamental principles of the universe, change our view of reality, and perhaps show us that most of what exists is still waiting to be discovered. What kind of matter could be out there, invisible to our eyes and telescopes, shaping the structure of the universe? This is the big question that has guided the search for the main candidates for dark matter. If ordinary matter, the stuff that makes up stars, planets, and even your own body, only represents a small fraction of the universe, what makes up that mysterious remainder? Scientists have proposed several possibilities, and each one seems straight out of science fiction. One of the most popular candidates is the so-called WIMPs, which stands for Weakly Interacting Massive Particles. Imagine a particle so elusive that it can pass through a lead wall kilometers thick without being detected. That's how faint its interaction with ordinary matter is. If WIMPs exist, they could fill the universe like an invisible fog, exerting gravity but without emitting or reflecting light. Their search has driven enormous underground experiments in mines and specially designed laboratories to detect the slightest hint of their presence. Another fascinating possibility is axions, even more exotic particles, so light that a single gram would contain an unimaginable number of them. Axions were originally proposed to solve a theoretical problem in particle physics, but soon became ideal candidates for dark matter. If they exist, they could be present in vast fields that span all of space, interacting with light in such a subtle way that they have eluded us until now. Some experiments are searching for axions, hoping to see how, under special conditions, these could transform into tiny flashes of light. But the list doesn't end there. Some have suggested the existence of particles called sterile neutrinos, even ghostlier versions of the already elusive neutrinos that constantly pass through the Earth. There has also been speculation about compact massive objects, like primordial black holes, although current evidence makes these options less convincing. Could dark matter be made up of a combination of different types of particles? It's a possibility that cannot be dismissed. What's intriguing is that, despite decades of searching, none of these particles have been directly detected. Are we searching in the right direction, or is dark matter playing a cosmic joke on us? The truth is that each of these candidates represents a doorway to an unknown universe, and their discovery would not only solve one of the greatest enigmas of astrophysics, but could also revolutionize our understanding of the very nature of reality. Why, if dark matter makes up the majority of the universe's mass, can't we see it? Is it possible for something so abundant to remain completely hidden from our eyes and our most advanced telescopes? To answer this paradox, it's crucial to understand what seeing something in the cosmos really means. When we talk about seeing, we refer to detecting the light, or any electromagnetic radiation, that objects emit, reflect, or absorb. However, dark matter plays by its own rules. It does not emit light, nor does it reflect or absorb it. It's as if there exists a type of matter that, although present, is invisible to all the senses that traditional astronomy uses. So, is dark matter some kind of perfect camouflage? Not exactly. More than camouflage, dark matter is transparent. It does not interact with light in any direct way. Imagine a room full of air. You know the air is there because you feel it, but you can't see it. Now imagine that you can't even feel the air, that you could only deduce its presence because papers and objects float or fall, as if an invisible force were pushing or stopping them. That's how ethereal dark matter is to us. We can only infer its existence from the gravitational effect it exerts on visible matter, like stars and galaxies. This lack of interaction with light is due to a fundamental characteristic. Dark matter is not composed of atoms like those that make up everything we know. Atoms, which form everything from a stone to our own bodies, are made of protons, neutrons, and electrons, and it is precisely these components that interact with light. Dark matter, on the other hand, would be made up of exotic particles that, according to current models, have no electric charge. By lacking an electric charge, these particles cannot absorb or emit photons, which are the particles responsible for light. Therefore, for dark matter, light simply passes by as if it doesn't exist. Could there be some type of light that dark matter does respond to? So far, all observations and experiments suggest that there isn't. Even in large particle accelerators, where attempts have been made to reproduce the necessary conditions to detect dark matter interactions, the results have been negative up to this point. This reinforces the idea that dark matter only reveals its presence through gravity. It's as if in the grand theatre of the cosmos, there is an invisible actor who never shows themselves but pulls the strings of the plot from the shadows, altering the fate of entire galaxies without us being able to observe it directly. The impossibility of seeing dark matter does not mean it is magical or impossible to study. In fact, its invisibility has spurred a scientific race to find new ways to detect it indirectly. Measuring galactic rotation curves, analyzing gravitational lenses, or exploring mysterious signals in underground detectors. But until we discover a way to interact with it directly, dark matter will remain, for us, the great shadow of the universe, present everywhere but always hidden from the light. What would happen if we removed dark matter from the universe? Although it may sound strange, without it, galaxies as we know them would never have existed. But why is this invisible component so crucial? The key lies in the way gravity acts on a large scale. If we only had visible matter, galaxies simply wouldn't have enough mass to hold their stars together. They would disperse before fully forming. Dark matter acts as an invisible scaffolding, a kind of cosmic web that provides the additional gravitational force necessary for galaxies to be born, grow, and remain cohesive. Now, how did we discover this fundamental role of dark matter? Astronomers observed that in the early moments after the Big Bang, the universe was primarily composed of a nearly uniform mix of matter and energy. However, small fluctuations in density allowed matter to begin clumping together. This is where dark matter comes into play. By not interacting with light, it could start collapsing and forming concentrations much earlier than ordinary matter. These seeds of dark matter attracted visible matter, accelerating the formation of the first galaxies and clusters. It's as if dark matter had marked the layout of invisible roads, guiding the construction of the galactic framework of the universe. And what evidence do we have of its influence? Modern cosmological simulations show that if we recreate the universe using only visible matter, the resulting structures are much smaller and more dispersed than what we actually observe. In contrast, by incorporating dark matter, the simulations manage to replicate the distribution of galaxies and clusters on a large scale with surprising accuracy. It's like comparing the structure of a building made only of bricks to one that also has hidden beams and foundations that provide strength and stability. Finally, dark matter not only influences the formation of individual galaxies, but also how they group into enormous superclusters and filaments. It forms the backbone of the universe, determining the architecture of the entire cosmos. Without dark matter, the universe would be a scattered ocean of stars, lacking the majesty of spiral galaxies and the complexity of the clusters that we are fascinated by in the maps of the sky today. How far does the structuring power of dark matter extend? We still don't know for sure, but each new observation reinforces the idea that this mysterious component has been the great architect behind the beauty and order of the universe. Is it possible to recreate the entire universe within a computer? Although it sounds like science fiction, astronomers and physicists have spent decades trying to do just that, using cosmological simulations to understand how the cosmos evolves, and in particular, how dark matter influences its structure. But why turn to these simulations? Because observing the real universe is like trying to reconstruct the history of a tree by only looking at its leaves. We need to see the whole forest, from its invisible roots to the farthest branches, and dark matter represents precisely those hidden roots. In a cosmological simulation, scientists input the known laws of physics, along with different amounts and distributions of dark matter, and then let the virtual universe evolve over billions of simulated years. What's the result? A digital cosmos that, incredibly, looks a lot like ours. The filaments of galaxies, the vast voids, and clusters like Coma emerge from these simulations only if dark matter is present. Without it, galaxies would scatter, and the large-scale structure of the universe simply wouldn't exist as we observe it. These simulations have allowed us to answer fundamental questions. Why do galaxies cluster in immense groups? How is it that enormous voids exist between them? Everything indicates that dark matter acts as an invisible scaffold, guiding the formation of galaxies and determining where they can grow and cluster. It's similar to how the shape of a mold determines the final appearance of a plaster figure. Visible matter occupies the space that dark matter allows, following patterns dictated by this mysterious substance. But simulations are not just theoretical tools. They also serve to test our hypotheses. When models do not match real observations, scientists adjust parameters, change the amount of dark matter, or alter its properties. What happens if another type of dark matter, lighter or heavier, is introduced? And what if its interaction with ordinary matter is modified? These virtual tests help rule out incorrect ideas and refine our understanding. Thus, cosmological simulations have become one of the most powerful laboratories for investigating dark matter, allowing exploration of possibilities that would be impossible to test in the real universe. Ultimately, thanks to simulations, scientists can observe the development of the universe from its earliest moments to the formation of clusters like Coma, and verify that without the presence of dark matter, the cosmos would be a radically different place. Although we still do not know exactly what it is made of, simulations show us time and again that the footprint of dark matter is essential to explain the complex architecture of the universe. Is dark matter and dark energy the same thing? Although their names may lead to confusion, they actually represent two of the greatest mysteries of the universe, but their nature and effects are completely different. To understand this difference, let's think of the cosmos as a huge stage. Dark matter would be the invisible scaffolding that holds galaxies and clusters together, while dark energy would be the mysterious force that pushes the expansion of the universe, increasingly separating those very scaffolds. Dark matter is a form of matter that neither emits, absorbs, nor reflects light. It is completely invisible to our telescopes. However, it exerts a very notable gravitational influence. It is responsible for galaxies rotating at speeds that would otherwise cause them to disintegrate. Without this ghost matter, cosmic structures could not remain united. In fact, approximately 1/4 of the universe's content is attributed to dark matter, which acts as the cosmic glue. On the other hand, dark energy is even more elusive and enigmatic. It represents about 2/3 of the universe, and its main effect is completely opposite to that of dark matter. While dark matter attracts, dark energy pushes. It is a kind of negative pressure that accelerates the expansion of the universe. An intriguing question is, how do we know it exists if we cannot see or touch it? The answer lies in the observation of distant galaxies. Astronomers have discovered that the universe is not only expanding, but doing so at an increasing rate, something that can only be explained if there is an unknown force driving that acceleration. It is common to wonder if there is any relationship between the two. The reality is that, although they share the surname dark, their origins and effects are distinct. Dark matter acts on the scales of galaxies and clusters, maintaining the cohesion of these systems. In contrast, dark energy operates on much larger scales, affecting the overall structure of the universe and its long-term fate. While one keeps the pieces of the cosmic puzzle together, the other seems to want to separate those very fragments. This contrast shows us that, in the universe, the invisible can be as influential as what we can see, and that many secrets remain to be discovered in the darkness of the cosmos. Few regions of the universe have been studied and observed as extensively as the Coma Cluster. But how has our view of this gigantic conglomerate of galaxies changed thanks to modern technology? Advances in optical and X-ray telescopes, as well as the use of radio telescopes and space observatories, have allowed astronomers to unravel previously invisible secrets, revealing a much more complex and fascinating picture of Coma. Today, thanks to these instruments, we know that the cluster is much more than a mere grouping of galaxies. It is a natural laboratory where dark matter plays a central role. How do we observe what we cannot see? Astronomers use the phenomenon known as gravitational lensing. When the mass of the cluster bends the light from more distant galaxies, it creates distortions in the images we receive. These distortions act as a kind of fingerprint of dark matter, allowing us to map its distribution in the cluster. Surprisingly, current maps show that most of the mass is in the form of dark matter, surrounding and permeating the cluster like an invisible fog. Additionally, X-ray telescopes have detected vast clouds of hot gas between the galaxies, whose temperature and behavior can only be explained if there is much more mass than what is directly observed. What are the most recent discoveries about Coma? Contemporary studies have identified violent interactions between galaxies, collisions, and mergers that generate shockwaves in the hot gas, observable thanks to space satellites. Filaments of dark matter connecting Coma to other nearby clusters have even been detected, revealing the existence of a cosmic web that supports the architecture of the universe on a large scale. These connections, invisible to the human eye, are inferred from the movements of galaxies and the behavior of interstellar gas. And what does the future hold for us? Next-generation instruments, such as ultra-sensitive radio observatories and next-generation space telescopes, promise to unveil even more details about the structure and evolution of Coma. Astronomers hope that by analyzing gravitational lenses at higher resolution and studying the radiation emitted by hot gas, they can refine dark matter maps and better understand the processes that govern the dynamics of clusters. The Coma Cluster remains an enigma, but each new observation brings us a little closer to deciphering the nature of dark matter and its fundamental role in the formation and stability of the universe. How is it possible to search for something that, by definition, cannot be seen or touched? That is the question that has driven scientists around the world to design extraordinary experiments to detect dark matter here on Earth. If dark matter makes up most of the mass of the universe, why don't we find it in our everyday surroundings? The key lies in its elusive nature. Dark matter does not emit, absorb, or reflect light, and barely interacts with ordinary matter. But physicists, far from giving up, have devised clever strategies to try to trap it indirectly. One of the most fascinating approaches involves building ultra-sensitive detectors located in protected places, such as underground mines or laboratories beneath mountains. Why so much effort to isolate them? Because dark matter, if it exists in the form of particles, could pass through the Earth without leaving a trace, as if millions of ghosts were crossing a solid wall without disturbing it. These laboratories search for minimal signals, a tiny vibration, a flash of light, or a slight increase in temperature caused by the hypothetical collision of a dark matter particle with atoms in a detector. It's like waiting for a coin randomly thrown from space to hit a bottle hidden in a cave. The xenon experiment, for example, uses enormous amounts of liquid xenon to catch the faintest of flashes. If a dark matter particle, such as a WIMP, weakly interacting massive particle, strikes a xenon atom, a detectable signal would be produced. But how do you distinguish that signal from all the noise in the environment? That's why scientists filter out any interference, from cosmic radiation to natural particles present in the atmosphere and soil, isolating the detector from almost the entire universe, except for dark matter. But not all experiments are searching for the same thing. Some, like Dama Libra in Italy, study seasonal patterns in the signals, under the hypothesis that the Earth, while orbiting around the Sun, might pass through currents of dark matter with varying intensity depending on the time of year. Other experiments, like Lux Zeppelin in the United States or Pandax in China, further refine sensitivity and increase the volume of detection material in an international race to be the first to capture an unequivocal signal. Although no experiment has yet succeeded in directly detecting dark matter, each attempt sharpens the limits of what is possible and rules out hypotheses. The search continues because finding a signal here on Earth could revolutionize physics and answer one of the greatest questions of the cosmos: what is the universe really made of? In this gigantic cosmic hide-and-seek, scientists do not give up and continue to fine-tune their antennas to catch the faintest whisper of dark matter, convinced that, at some point, the universe will reveal one of its most enigmatic pieces. What relationship could an invisible substance have with the fate of the entire universe? The answer lies in dark matter and its influence on cosmic expansion. Although we cannot see it, dark matter is a fundamental part of the cosmos's balance, acting like an invisible skeleton that supports the largest structures in the universe. But how does this mysterious substance affect the very expansion of space? To understand this, we must first remember that the expansion of the universe is like a race between gravity and the energy driving the separation of galaxies. In this duel, dark matter plays a crucial role. For billions of years after the Big Bang, dark matter had a braking effect on expansion. Gravity, generated by both visible and dark matter, acted as a brake, trying to slow down that accelerated growth of space. A universe composed solely of visible matter would not have enough gravity to form clusters of galaxies or to significantly oppose expansion. However, the enormous amount of dark matter, whose mass is much greater than that of stars and gas, provided the necessary weight for galaxies and clusters to remain cohesive, and for expansion not to run rampant from the beginning. But what is happening now? Today we know that the expansion of the universe is accelerating, a phenomenon attributed to dark energy, which acts in opposition to gravity. However, dark matter remains essential. It determines the speed at which expansion shifted from slowing down to accelerating. We could imagine it as a tug-of-war competition between two teams. One, dark matter, pulling to slow down expansion, and the other, dark energy, pulling in the opposite direction. The exact amount of dark matter is key to understanding when and how dark energy began to win that battle, causing the acceleration we observe today. Dark matter also shapes how the expansion of the universe leaves its mark on large-scale structure. Areas where dark matter concentrated served as seeds for the formation of galaxies and clusters. If there were less dark matter, the universe would be much more homogeneous, without large structures, and expansion would have eliminated the possibilities of planets, stars, and life as we know it forming. Therefore, dark matter not only influences the speed of expansion, but also determines the complexity and diversity of the cosmos. So, could the final fate of the universe depend on dark matter? In a way, yes. The total amount of dark matter conditions, whether the universe will expand forever, slow down, or even collapse in the distant future. Although dark energy seems to dominate today, the influence of dark matter was and continues to be vital in defining the history and future of everything that exists. Thus, dark matter, invisible and elusive, is one of the great protagonists in the expansion and ultimate fate of the universe. What keeps a galaxy cluster like Coma together against the titanic force of the universe's expansion? It's a question that puzzles even the most experienced astronomers. If we think of a galaxy cluster, we might imagine it as a swarm of bees buzzing in space, each moving at high speed. However, the gravity exerted by the visible galaxies, along with the hot gas between them, is not enough to prevent the cluster from dispersing. So, what holds this gigantic cosmic structure together? The key lies in dark matter. Although we cannot see or detect it directly, its gravitational influence is so powerful that it acts like an invisible glue, keeping hundreds, even thousands of galaxies bound together within the Coma Cluster. To put it into perspective, calculations indicate that the total mass needed to keep these galaxies clustered is at least 5 times greater than all the combined visible matter. Without that extra mass, the galaxies would simply drift away, as if an invisible tether suddenly snapped. But how do we know dark matter is there if we can't see it? Astronomers analyze the speeds at which the galaxies move within the cluster. If only luminous matter existed, those speeds would be much lower. The fact that they are so high indicates the presence of a large amount of hidden mass. It's like playing tug of war with our eyes closed and noticing that someone else is pulling hard, even though we can't see them. Only dark matter can explain that additional force needed to keep the cluster from collapsing. Dark matter, then, is essential for the stability of galaxy clusters. Without it, the largest structures in the universe would not have survived from their origins to today. Ultimately, the existence of clusters like Coma is one of the strongest pieces of evidence for the presence of this mysterious matter. Dark matter not only shapes galaxies, but is also responsible for keeping clusters as true cosmic cities, resisting the passage of time and universal expansion. Is dark matter really only present in the Coma Cluster, or are there signs of its existence in other corners of the universe? The answer is fascinating. The evidence of dark matter extends far beyond a single cluster, appearing as an enigma that envelops almost all known galaxies. If we observe spiral galaxies, for example, an intriguing mystery arises. Why do the stars on the outer edges of these galaxies rotate almost at the same speed as the stars closer to the center, even though, according to the gravity of the visible mass, they should be moving much more slowly and even escaping the galaxy? It's as if a carousel spins and the horses on the edge move just as fast as those in the center, something completely counterintuitive. This strange regularity in galactic rotation curves was detected by astronomers like Vera Rubin in the second half of the 20th century. Her measurements revealed that luminous matter, the kind we can see and quantify, is not enough to explain the behavior of the stars. So what holds these galaxies together, preventing them from disintegrating under centrifugal force? Everything points to a vast amount of invisible matter, dark matter. This phenomenon is not exclusive to a particular galaxy, but is repeated in the Milky Way, in Andromeda, and in countless distant galaxies, suggesting that dark matter is a universal and essential ingredient for the stability of galactic systems. But traces of dark matter are not limited to rotation curves. When astronomers study elliptical and dwarf galaxies, or analyze mergers between galaxies, they find more indirect evidence. In collisions like the so-called bullet cluster, the visible matter, primarily composed of hot gas, separates after the impact, while most of the mass seems to pass through the collision without friction. It's as if 2 cars collided and the body flew off in one direction, but most of the invisible mass continued on as if nothing had happened. Observations of gravitational lensing in these systems reinforce the idea that there is a massive and transparent substance dominating the cosmic scene. Could all this be due to our misunderstanding of gravity on a large scale? Some scientists have proposed alternative theories, but the coincidence and consistency of dark matter traces in galaxies of all types and in distant clusters reinforce the thesis of its existence. Through different methods, such as analyzing the velocities of stars, the distortion of light by gravitational lenses, and the dynamics of galactic groupings, the universe seems to be speaking to us in a clear language. Dark matter is everywhere, shaping the architecture of the cosmos and leaving its traces in every galaxy we observe. What if dark matter, that enigmatic invisible component of the universe, didn't actually exist? This question has driven some scientists to seek alternative explanations. The most well-known of these theories is MOND, which stands for Modified Newtonian Dynamics. What does it entail? Basically, MOND suggests that the laws of gravity do not behave exactly the same at large cosmic scales as they do at the scales we experience on Earth. It's as if gravity plays by its own rules when it comes to galaxies or massive clusters. Instead of assuming there is a large amount of invisible matter, MOND adjusts Newton's equation to explain why galaxies rotate faster than they should based on the amount of visible matter. But can a simple modification of gravity explain all the mysteries? Although MOND had some success in reproducing the rotation curves of certain galaxies, cracks soon began to appear in its structure. For example, when it comes to more complex systems like galaxy clusters, MOND fails to account for all the missing mass. Additionally, gravitational lensing phenomena, where light from distant objects bends when passing near large concentrations of mass, seem to require more matter than MOND can explain with just its adjustment of gravity. Another alternative proposal has been the existence of baryonic dark matter, that is, ordinary matter, but difficult to detect, such as wandering planets, brown dwarfs, or clouds of cold gas. However, studies on the abundance of light elements created during the Big Bang, like hydrogen and helium, show that there simply isn't enough ordinary matter to explain the behavior of galaxies and clusters. It's like searching for lost keys only under the light of a street lamp, because it's easier to see there, ignoring that they are likely in the dark. Are there other ideas? Yes, some theories even challenge our most basic ideas about space-time, proposing additional dimensions or unknown interactions. However, so far, no alternative has successfully explained all the observed phenomena, from the formation of large-scale structures to galactic rotation curves to the effects of gravitational lensing. That's why, although dark matter remains a mystery, most astronomers consider it the most robust explanation with current evidence. Still, science never stops questioning and seeking new answers, because the universe is an expert at challenging our limits. Have you ever wondered if dark matter and gravitational waves are related? Although they seem like separate concepts, both represent great enigmas of the cosmos and, interestingly, could help each other reveal hidden secrets of the universe. Gravitational waves, those ripples in the fabric of space-time predicted by Einstein, have allowed science to observe previously invisible phenomena, such as the merging of black holes. But could they also give us clues about the mysterious dark matter? Dark matter does not emit or reflect light, and so far, all attempts to detect it directly have been unsuccessful. However, astrophysicists believe that if dark matter interacts with gravity, then its presence should influence the propagation of gravitational waves through space. Think of it like sound traveling through different materials. The echo changes depending on what it encounters along the way. Similarly, a gravitational wave traveling through regions dense in dark matter could show subtle alterations in its shape or speed. This has led to a fascinating question. Can we use gravitational waves as a kind of cosmic radar to map dark matter? There are already theoretical proposals suggesting that if two massive objects, like black holes or neutron stars, collide in regions rich in dark matter, the pattern of the emitted gravitational waves could differ from what is expected in areas where dark matter is scarce. Thus, carefully analyzing the waves that reach Earth could allow scientists to deduce the amount and distribution of dark matter in those remote areas of the universe. Another intriguing hypothesis is that dark matter could be partially composed of compact objects, like primordial black holes. If this were true, collisions of these objects would produce gravitational waves with unique characteristics that we could identify. What if, at some point, we detect a signal that doesn't fit with what we know? It could be the signature of dark matter manifesting in a completely unexpected way. Although we have not yet found direct evidence of this scenario, the combination of gravitational wave astronomy and the study of dark matter opens a new window to explore the hidden side of the cosmos. In summary, gravitational waves not only tell us stories about cosmic cataclysms, but could also be our allies in unraveling the secrets of dark matter. Each new detection is like receiving a mysterious letter from the far reaches of the universe, a letter that may one day contain the key to solving one of the greatest enigmas of modern physics. Are there particles in the universe that are almost invisible, yet have a fundamental impact on cosmic structure? Neutrinos are one of the most fascinating and mysterious candidates in the realm of physics and cosmology. These tiny particles, nearly massless and traveling close to the speed of light, pass through ordinary matter as if it didn't exist. Every second, trillions of neutrinos cross our bodies without us noticing. But could neutrinos be responsible for the dark matter that holds galaxies and clusters like Coma together? The answer is not so straightforward. Neutrinos, being so light and moving so fast, are considered a form of hot dark matter. This means that, in the early moments of the universe, these neutrinos were so swift that they could not easily clump together to form structures like galaxies and clusters. It's like trying to build sandcastles with grains that never stop moving. They simply don't stay still long enough. Therefore, although neutrinos contribute to the total mass of the cosmos, they cannot alone explain most of the dark matter, which appears to be cold and capable of massive clumping. However, neutrinos are not entirely ruled out. We know, thanks to experiments like the Sudbury Neutrino Observatory and Super Kamiokande in Japan, that neutrinos have mass, albeit incredibly small. This mass, combined with the unimaginable number of neutrinos in the universe, contributes a significant fraction to the total invisible mass. But here arises a crucial question. If neutrinos are not the main form of dark matter, what role do they really play in the balance of galaxy clusters? Scientists have discovered that neutrinos affect the evolution of the universe on a large scale. Their presence influences how galaxies are distributed and the imprints they left on the cosmic microwave background. Moreover, the study of neutrinos has opened the door to new questions about particle physics and the composition of the universe. Could there be a type of neutrino that is even more elusive, perhaps heavier, that is part of cold dark matter? This question keeps physicists and astronomers in a constant search for answers, exploring both the cosmos and underground laboratories on Earth. Neutrinos, though small and elusive, remain key pieces in the puzzle of dark matter, reminding us that the universe hides secrets in the most unsuspected places. What if I told you that the light traveling through the universe doesn't always follow a straight path? The presence of dark matter in galaxies acts like a kind of invisible sculptor, shaping the trajectory of light rays coming from distant stars. Although dark matter does not emit, absorb, or reflect light, its gravity does have the ability to influence how light moves. It's as if light were a river and dark matter, a series of rocks hidden beneath the water, diverting the current without being seen. How does this affect our view of the cosmos? When astronomers observe distant galaxies, they often notice that the light we receive from them is distorted or even duplicated. This phenomenon is known as gravitational lensing, and it is a direct consequence of the gravitational influence of dark matter. Imagine looking through a glass cup. The objects on the other side may appear stretched, curved, or multiplied. The same happens on cosmic scales, where dark matter curves space-time and forces light to follow unexpected paths. But dark matter doesn't just distort the light from distant galaxies. It also affects how light is distributed within the galaxies themselves. For example, if only visible matter existed, galaxies should rotate much more slowly at their outer edges. However, the light shows that stars at the edges rotate almost as fast as those in the center, which can only be explained if there is an invisible mass, dark matter, keeping them together. Thus, the distribution of light in a galaxy serves as an indirect clue to the existence of that hidden matter. Is it possible, then, that dark matter is hidden in every astronomical image we see? Every time we analyze the light from a galaxy, we are deciphering a code that reveals not only the presence of stars and gas, but also the silent trace of dark matter. Its influence is so profound that without it, the structure and beauty of galaxies as we know them would be impossible. Dark matter, though invisible, leaves its mark on the light itself, telling us the story of a universe much more mysterious than our eyes can perceive. What clues can the cosmic microwave background give us about dark matter? This faint glow, which has filled the universe for nearly 14 billion years, is much more than a distant echo of the Big Bang. It is, in fact, a kind of cosmic fingerprint that contains precise information about the composition and early evolution of the cosmos. When scientists analyze the tiny temperature variations in this background, they are deciphering ancient codes that reveal how much visible matter and how much dark matter existed in the universe's earliest moments. Why is the cosmic microwave background so important in this search? Because in its tiny fluctuations lies the answer to a crucial question. How much dark matter was there in the primitive universe? The small differences in temperature and density that we see in the cosmic background are not random. They are the result of the interaction between normal matter, dark matter, and radiation in the first few 100,000 years after the Big Bang. It's as if the universe had been a calm lake that, when disturbed, recorded the ripples of every stone thrown. Those ripples, frozen in the cosmic background, contain the signature of dark matter. Scientists have used satellites like COBE, WMAP, and Planck to accurately map these fluctuations. What have they discovered? That dark matter represents approximately 5 times more than visible matter in the universe. But the most interesting part is how they reach this conclusion. By comparing the observed patterns in the cosmic background with theoretical models, they realized that only the presence of a large amount of invisible matter could explain the distribution and intensity of the ripples. If only ordinary matter existed, the structures would be very different, much less defined, and more chaotic. And what role does dark matter play in the formation of the first cosmic structures? Without it, galaxies and clusters would not have been able to form as we know them. Dark matter acted as an invisible scaffold that attracted normal matter, allowing the seeds of galaxies to grow in the fabric of the primitive universe. Thus, by analyzing the cosmic microwave background, we not only confirm the existence of dark matter, but also understand its indispensable role in the evolution of the cosmos. Every little cold or hot spot in that background is, at its core, a clue about the mystery that continues to surround dark matter. What does the future hold for the research of the Coma Cluster and its mysterious dark matter? The answer to this question is one of the great driving forces of modern astrophysics. Scientists are developing new strategies and technologies to unravel the hidden secrets in this gigantic cluster of galaxies. But how can the invisible be studied? The key lies in observing with unprecedented precision the movements of galaxies and the gravitational effect that dark matter has on light and the cosmic environment. In the coming years, next-generation telescopes like the James Webb, the Vera Rubin Observatory, and space missions like Euclid will allow us to capture even more detailed data on the distribution of mass and energy in Coma. Could a new theory about gravity or matter revolutionize everything we think we know? Researchers are not only looking to accumulate more data, but also to challenge traditional models. Some teams analyze the subtle distortions in the light from distant galaxies, the so-called gravitational lenses, to map dark matter with astonishing detail. Others focus on particle physics, hoping that an experiment on Earth, such as dark matter detectors buried under mountains, will succeed in recording an elusive particle that confirms once and for all the nature of this invisible component. What if the Coma Cluster holds clues about processes still unknown in the evolution of the universe? One of the great hopes is that by studying the differences in the distribution of dark matter between clusters like Coma and other systems, patterns can be identified that reveal new physical laws or even the existence of new particles. Each new observation is like finding a piece of a cosmic puzzle in which many shapes are still waiting to be discovered. In short, the future of research in Coma is a long-distance race that combines advanced observation, theoretical physics, and international collaboration. The question is not only what dark matter is, but how its study can transform our image of the universe. Are we on the brink of a scientific revolution? No one knows, but the coming decades promise discoveries that could forever change the way we understand reality. What would happen if dark matter didn't exist? Would the universe be as we know it? Dark matter, that mysterious invisible component, has played a fundamental role in the history and fate of the cosmos. Without it, galaxies would not have been able to form as coherent structures. In fact, the gravity generated solely by visible matter would be insufficient to keep them together. Stars and planets would be too dispersed, and the universe would be a much more chaotic and empty place. It's like trying to build a sandcastle on the beach without water. The grains don't stick together, and the structure simply can't hold. But the role of dark matter is not limited to just galaxy formation. Its influence extends to the very evolution of the universe. Dark matter acts as a kind of cosmic scaffolding, providing the structure that guides the growth of galaxy clusters and the large-scale distribution of matter. Filaments of dark matter connect galaxies and clusters, forming a cosmic web that has defined the landscape of the universe since its earliest moments. If we could see dark matter, the universe would appear to us as a gigantic three-dimensional spiderweb, where each node is a cluster of galaxies held together by this invisible mass. How does this affect life and our own place in the cosmos? The answer is deeper than it seems. Without dark matter, the density of galaxies in the universe would be much lower, and the formation of stars and planets would be a rare event. Life, at least as we imagine it, might never have emerged. It's fascinating to think that the forces and particles we cannot directly detect have been crucial for the existence of elements, solar systems, and ultimately, ourselves. Dark matter has created the conditions for life to emerge on planets like Earth, billions of years after the Big Bang. And what does the future hold for us? Dark matter also influences the ultimate fate of the universe. Although we still do not know its exact nature, its presence affects the rate of expansion of the cosmos and the evolution of large structures. Will the universe collapse at some point, or will it continue to expand forever? The answers depend in part on how much dark matter exists and how it interacts with dark energy. Thus, this invisible element remains one of the key pieces to understanding not only the origin and evolution of the universe, but also its final destiny. The life of the cosmos, from the first spark to the last breath, is deeply intertwined with the mystery of dark matter. Is it true that dark matter could be some kind of exotic matter that completely challenges our understanding of physics? This is one of the most common questions, and while dark matter is mysterious, it doesn't mean it's magical or violates the laws we already know. The term dark does not imply that it is related to darkness or the supernatural, but rather that it simply does not emit, absorb, or reflect light, making it invisible to our telescopes. In reality, scientists are seeking explanations that fit within the framework of known physics, even as they explore the limits of what we know. Many believe that dark matter is a tangible substance that we could touch if we had the right technology. But could we really hold a piece of dark matter in our hands? The reality is that, so far, dark matter does not interact with ordinary matter in any significant way, except through gravity. It's like trying to catch the wind in a fishing net. We know it's there by its effects, but we cannot catch it or observe it directly. This is why terrestrial experiments, despite decades of attempts, have yet to achieve direct detection. There is also the belief that dark matter is responsible for all cosmic mysteries, from black holes to dark energy. However, this is a myth. Dark matter and dark energy are completely distinct concepts. The former acts as an invisible glue that holds galaxies and clusters together, while dark energy drives the accelerated expansion of the universe. They are not the same, nor do they serve the same role in cosmic evolution. Confusing these two concepts is as erroneous as assuming that air and water have the same function just because both are invisible to the naked eye. Another frequent question is whether dark matter could, at some point, become dangerous to humanity or alter life on Earth. The answer is that there is no evidence that dark matter interacts with living beings in any perceptible way. Its influence is on a grand scale, shaping cosmic structures and galactic trajectories, but it literally goes unnoticed at the human level. Even if a cloud of dark matter were to pass through our planet right now, we would not notice anything at all. Thus, dark matter, far from being a threat, is a key and silent piece in the great puzzle of the universe. What makes the Coma Cluster so fundamental in the development of modern astrophysics? To answer this question, it is necessary to remember that, in the history of astronomy, there are discoveries that act as hinges. Before them, the universe seemed one way. After, everything changed. Coma is precisely one of those hinges. Not only was it the setting where the first great evidence of dark matter emerged, but it also transformed into a natural laboratory to test fundamental theories about the structure and evolution of the cosmos. The Coma Cluster became the starting point for understanding that visible matter is just a small part of the cosmic equation. Why did astronomers deduce that something invisible must be there? By analyzing the speeds at which galaxies move within the cluster, calculations showed that if only the matter we can see existed, these galaxies would simply escape. It's like trying to keep a swarm of bees together with a net made of threads that are too fine. Inevitably, they would scatter. But in Coma, the galaxies remain bound together thanks to an additional force, invisible yet decisive. This phenomenon forced the scientific community to rethink the very nature of the universe. From Coma, innovative techniques were developed to measure masses and detect gravitational phenomena that could not be observed directly. The cluster served as a testing ground for the use of gravitational lenses, allowing astronomers to map the distribution of dark matter with unprecedented precision. Moreover, observations of Coma inspired the development of computational simulations that are now key tools for recreating the evolution of the universe, from its earliest moments to the formation of the large structures we see today. Over the past few decades, the study of the Coma Cluster has driven advances in astronomical instrumentation, gravity theory, and cosmology. Each new observation of Coma raises even deeper questions. What is dark matter really made of? Is it possible that there are unknown new particles? Or do we need to modify physics as we know it? Coma, far from being just a cluster of galaxies, has become the epicenter of a scientific revolution, a constant reminder that the universe holds secrets yet to be deciphered. Its role in modern astrophysics is, without exaggeration, that of a beacon guiding the search for answers to the greatest mysteries of the cosmos. Detecting dark matter is one of the greatest challenges of modern physics. Why is it so difficult to find something that, in theory, makes up most of the matter in the universe? The answer lies in the elusive nature of dark matter itself. It neither emits, absorbs, nor reflects light, making it invisible to all traditional telescopes. It's like searching for a needle in a haystack. When the needle is invisible, has no smell, no weight, and can pass through the haystack without leaving a trace. The instruments we use to study the cosmos are designed to capture electromagnetic signals, but dark matter seems to completely ignore them. Could we then capture dark matter particles using detectors on Earth? That has been one of the main approaches in research, but here arises another major obstacle. Dark matter is expected to interact extremely weakly with ordinary matter. To detect it, underground laboratories must be built to block any background noise, such as cosmic particles, and even then, experiments barely manage to distinguish any significant signal from the incessant sea of radiation and particles that surrounds us. It's like hearing the soft buzz of a mosquito in the midst of a thunderstorm. Interpreting the results also presents difficulties. How can we know if the detected signal truly comes from dark matter or is the result of an unknown particle, an instrumental failure, or even a statistical fluctuation? Many experiments have reported possible hints of dark matter that, when repeated, fail to be confirmed. Moreover, there are different theories about what dark matter actually is. From massive, slow particles like WIMPs to extremely light particles like axions. Each type requires different detection strategies and technologies, multiplying the complexity of the challenge. As if that weren't enough, technological advancements must always stay one step ahead of the mystery. Scientists are working on designing increasingly sensitive and sophisticated instruments, but dark matter always seems to slip through their fingers like fine sand. What if dark matter does not interact at all with ordinary matter, except through gravity? In that case, all our direct experiments would be useless, and we would have to rely solely on indirect observations, such as gravitational effects on galaxies and clusters. Thus, the search for dark matter becomes a constant race against the unknown, demanding both creativity and patience from those who dare to confront one of the greatest enigmas of the universe. Who are the protagonists in the hunt for dark matter? Although dark matter is invisible and mysterious, the search for its secrets has summoned a global network of scientists, engineers, and observatories that collaborate as if they were pieces of a giant puzzle. No one can solve this mystery alone. That's why international projects unite resources, talents, and technologies from multiple countries, from laboratories beneath mountains to space telescopes, in a true scientific crusade. Where are these great efforts located? In the heart of Europe, CERN brings together thousands of researchers from around the world to analyze particle collisions that could provide clues about dark matter. In the United States, projects like Lux Zeppelin and the Xenon experiment have placed enormous tanks of liquid xenon underground, shielding them from cosmic radiation to detect the elusive particles that are suspected to make up dark matter. In Japan, the Super Kamiokande experiment searches for indirect signals of these mysterious cosmic components, while in South America, the Pierre Auger Observatory studies ultra-high-energy cosmic rays that could be related to processes where dark matter plays a role. But how do they coordinate so many minds and resources scattered across the planet? Through formal collaborations, international conferences, and the open exchange of data and results. It is common for a scientific publication on dark matter to include hundreds of authors from different countries. Teams share software, analysis techniques, and even components of detectors. This cooperation transcends languages, borders, and cultures, driven by the common ambition to answer one of humanity's oldest questions: what is the universe really made of? And how far have we come thanks to this teamwork? Although dark matter remains the great enigma, the advances made have only been possible due to this collective effort. International agreements allow for the construction of larger and more sophisticated detectors and expand the range of observation, as is the case with telescopes like the Vera Rubin Observatory, which will soon map the entire sky in search of traces of dark matter in the distribution of galaxies. If we ever manage to directly detect a dark matter particle, it will be the result of a true global collaboration, a testament to how science unites humanity in the face of the mysteries of the cosmos. Why is dark matter considered one of the key pieces in modern cosmology? The answer lies in its fundamental role as the invisible scaffolding of the universe. Without dark matter, galaxies simply could not exist as we know them today. If we imagine the universe as a gigantic spiderweb, dark matter would be the thread that holds the entire structure together, allowing visible matter, like stars and planets, to cluster and form complex systems. Without this mysterious substance, the gravity of ordinary matter would not be enough to bind galaxy clusters and keep them stable over billions of years. But how did we come to know this? Astronomers observed that when calculating the mass of galaxies and clusters based solely on visible matter, the numbers didn't add up. The rotation speeds of galaxies were so high that, according to classical physics, they should have dispersed. This led to the conclusion that there must be a large amount of invisible matter exerting additional gravity. This idea revolutionized our understanding of the cosmos and opened a new branch of physics and astronomy dedicated to exploring what we cannot see, but can measure by its effects. The importance of dark matter is not limited to the stability of galaxies. It also plays a crucial role in the formation of the first structures after the Big Bang. According to the most advanced cosmological simulations, dark matter acted as a kind of gravitational seed, around which primordial gas began to cluster. This allowed for the formation of the first stars and galaxies much earlier than would have been possible with normal matter alone. Without dark matter, the universe would be a much more homogeneous and dull place, lacking the diversity of structures we observe today. Can cosmology understand the ultimate fate of the universe without considering dark matter? Practically not. Dark matter not only influences the evolution of galaxies and clusters, but also affects the expansion of the universe alongside other components, such as dark energy. All modern theories about the evolution and future of the cosmos critically depend on knowing the amount and distribution of dark matter. Thus, dark matter is not just a scientific curiosity, but an essential element for deciphering the past, present, and fate of the universe. Its study remains one of the greatest challenges in science, and any advancement in its understanding could radically change our view of the cosmos. What happens when astronomers decide to closely observe a galaxy cluster like Coma, hoping to find answers, but instead encounter new questions? Over the decades, the Coma Cluster has proven to be an inexhaustible source of surprises for the scientific community. One of the most unexpected discoveries was the identification of ultra-diffuse galaxies, systems so faint and extended that they went unnoticed for a long time. How is it possible that these galaxies, almost invisible even to the most powerful telescopes, survive in such a hostile environment as the Coma Cluster? The existence of these structures suggests that dark matter plays an even more fundamental role than previously thought, acting as an invisible glue that holds these ghostly galaxies together, preventing them from being torn apart by the gravitational forces of the cluster. Another intriguing revelation came when scientists began to map the distribution of dark matter in Coma using gravitational lensing techniques. What did they find? Dark matter is not distributed evenly. Instead, it concentrates in filaments and cores, forming a kind of cosmic web that connects different regions of the cluster. This structure resembles a three-dimensional spider web, where visible matter is barely the dust on the threads. This finding has propelled new theories about how matter clusters in the universe and has forced astrophysicists to reconsider how they interpret the evolution of large galaxy clusters. But the mysteries don't end there. In recent studies, unusual movements have been detected within the Coma Cluster, as if some of its galaxies were moving at unexpectedly high speeds or following strange trajectories. Could these behaviors be signs of past collisions, or perhaps indications of the presence of dark matter substructures that we do not yet understand? This type of discovery has opened the door to the idea that the Coma Cluster is much more dynamic and chaotic than previously thought, challenging the traditional image of a system in equilibrium. Finally, a surprising finding emerged when analyzing the composition of the hot gas filling the cluster. Fluctuations and shock waves have been detected that suggest large amounts of energy are being released in processes that are still not fully explained. Could it be that dark matter interacts in some unknown way with ordinary matter, causing these effects? Or perhaps we are witnessing the traces of extreme cosmic events, such as mergers between giant galaxies. Each of these unexpected discoveries in Coma reminds us that, in the universe, answers are never definitive. There is always a new enigma waiting to be revealed. Why has dark matter captured the imagination of so many people outside the scientific realm? Perhaps it's due to that sense of unfathomable mystery, the idea that there is something invisible holding the universe together yet we cannot see or touch it. This notion, so close to great enigmas and myths, has inspired countless stories, books, movies, and even video games. In popular culture, dark matter often transforms into a narrative device that represents the unknown, the dangerous, or even the magical. For many screenwriters and authors, it is the perfect excuse to introduce hidden dimensions, inexplicable powers, or cosmic threats that defy logic. Have you noticed how many science fiction movies mention dark matter as a source of energy, a gateway to other universes, or even as the origin of mysterious creatures? On the big screen, dark matter takes on almost supernatural properties. It can enable interstellar travel, generate impossible weapons, or unleash cosmic disasters. A clear example is how in some superhero sagas, dark matter becomes the trigger for superhuman powers or events that completely escape known physics. Thus, real science and fiction intertwine, and the general audience begins to associate dark matter with all kinds of fantastic phenomena. But is this an exaggeration, or does it help bring science closer to the public? Interestingly, although many representations of dark matter in popular culture are not rigorous or are outright fantastical, they have contributed to millions of people hearing about this concept for the first time. It's as if dark matter has become a bridge between scientific mystery and human creativity. Through novels, comics, and series, people become familiar with the idea that the universe is much more complex than it appears at first glance, and that there is still much to discover. However, it is worth asking, do these fictional versions help or confuse? On one hand, they spark curiosity and motivate many to investigate beyond the screen or the pages. On the other, they can generate misconceptions, such as assuming that dark matter is something tangible or easily manipulable, when in reality, scientists have not even managed to detect it directly. Ultimately, dark matter in popular culture serves as a powerful metaphor for the unknown, a reminder that, both in science and in imagination, there are always unanswered questions waiting to be explored. What are the next steps in the search for dark matter? What horizons await science in this mysterious frontier? Astronomers and physicists around the world are faced with an enigma that challenges our most basic understanding of the universe. If dark matter makes up most of the mass of the cosmos, how is it possible that we still do not know what it is made of or how to detect it directly? This question drives a genuine global scientific race, where every advance could mean a leap in our vision of the universe. In the coming years, one of the great hopes lies in direct detection experiments, buried under mountains or in underground laboratories, shielded from cosmic radiation. These detectors search for tiny signals, like the faint collision of a dark matter particle with a liquid xenon atom, hoping to capture that unique moment that confirms its existence. What if dark matter interacts so weakly that it will never be possible to detect it this way? In this scenario, scientists are exploring alternative routes. From the search for new particles in colliders like the Large Hadron Collider, to the observation of unexpected cosmic signals, such as gamma rays or neutrinos, coming from places where dark matter might be accumulating and annihilating. Another promising perspective lies in the analysis of data obtained by increasingly powerful telescopes. Upcoming space and ground observatories, such as the Vera Rubin telescope, will allow for an unprecedented mapping of the distribution of dark matter in galaxies and clusters. Could these maps reveal hidden patterns or anomalous behaviors that bring us closer to the true nature of this invisible matter? Just like assembling a puzzle with transparent pieces, astronomers must look for indirect traces. How light paths bend, how galaxies cluster, how cosmic microwaves fluctuate. However, not all scientists bet that dark matter is an unknown particle. A growing group is exploring the possibility that, in reality, the laws of gravity need to be modified on cosmic scales. What if the problem is not the existence of invisible matter, but that our understanding of gravity is incomplete? Theories like modified gravity have gained traction, although they still do not explain all observed phenomena. The future of research could bring about a theoretical revolution that changes the game, just as the theory of relativity did over a century ago. In short, dark matter represents one of the greatest challenges and opportunities in modern physics. Its search could not only reveal what composes most of the universe, but also open doors to completely new physics, with unforeseen implications for technology and philosophy. Are we on the verge of discovering the missing piece in the great cosmic puzzle, or is an even deeper mystery awaiting us? The only certainty is that every discovery, every experiment, and every hypothesis pushes us one step closer to understanding the true fabric of the universe. Can an invisible mystery hold the fates of entire galaxies? Dark matter, that elusive entity, remains one of the greatest enigmas of the universe. We know it's there because we feel its influence. It keeps cosmic structures together that would otherwise scatter under the force of their own gravity. But how is it possible that something we cannot see, touch, or detect with our most advanced instruments is so fundamental to the very existence of the cosmos as we know it? If we imagine the universe as a play, dark matter would be the scaffolding hidden behind the curtain. Without it, galaxies and clusters could not perform their roles. Their shapes would crumble, their gravitational dances would cease to make sense. And yet, no matter how much we search, we can only infer its presence from the effects it generates. Could it be that what we call dark matter is merely a reflection of a physics still unknown? Or is there really an invisible ocean of particles waiting to be discovered? The paradox becomes even more fascinating when we observe clusters like Coma, where the visible mass is barely the tip of the iceberg. What else does the universe hide beneath that luminous surface? Every calculation, every observation leads us to an inescapable conclusion. Most of the matter that shapes the universe is literally invisible. It's as if we were trying to reconstruct a story only with the shadows cast on a wall, knowing that the real source remains hidden. Despite technological advances, every answer we obtain seems to open even more questions. What is dark matter really? Will we ever be able to detect it directly? Or are we destined to coexist with this cosmic shadow, aware of its existence, but unable to unveil its true nature? The paradox of dark matter remains alive. It is a reminder that, although we have made great strides in our understanding of the universe, there are still frontiers that remain unexplored, waiting for human curiosity to take the next step toward discovery.